Have you ever wondered how your graphics card can render stunning 3D worlds in real time? The modern GPU is an engineering marvel, capable of performing trillions of calculations per second. Today we're going to dive deep into how graphics cards work, exploring both their physical components and computational architecture. Let's start with a mind-boggling fact. High-end graphics cards today can perform over 36 trillion calculations per second. To put that in perspective, if every human on Earth did one calculation per second, we would need about 4,500 Earths worth of people to match a single modern GPU. That's the kind of computational power we're talking about. But why do we need such incredible processing power? Well, modern video games and applications demand it. The days of simple 2D sprites are long gone. Today's games feature photorealistic lighting, complex physics simulations, and detailed 3D models with millions of polygons. All of this requires massive parallel processing power that only a GPU can provide. So what exactly is a GPU, and how does it differ from the CPU in your computer? While both are processors, they're designed for fundamentally different tasks. The CPU, or Central Processing Unit, is the general-purpose brain of your computer. It typically has a small number of very powerful cores, maybe 4, 8, or 16 in modern systems, that can handle a wide variety of tasks. CPUs excel at sequential processing, where one calculation leads to the next. GPUs, on the other hand, are specialized processors designed specifically for parallel computing. They contain thousands of relatively simple cores that work simultaneously on different parts of the same problem. This makes them ideal for graphics rendering, where the same operation needs to be performed on thousands or millions of pixels or vertices at once. Think of it this way: a CPU is like a few master chefs in a kitchen, capable of preparing complex dishes from start to finish. A GPU is like an assembly line of hundreds of cooks, each performing a simple task over and over again. For certain tasks, that assembly line approach is vastly more efficient. Now, let's open up a modern graphics card and see what's inside. The main component is the GPU chip itself, a silicon die packed with billions of transistors. For example, NVIDIA's G102 chip used in the RTX 3090 contains a staggering 28.3 billion transistors. That's more than 4 times the number of people on Earth, all packed into a chip smaller than your palm. The GPU chip is organized hierarchically. At the highest level, it's divided into graphics processing clusters, or GPCs. Each GPC contains multiple streaming multiprocessors, SMEs, which in turn contain the actual processing cores. In the RTX 3090, there are over 10,000 CUDA cores, which are the basic computational units of the GPU. These CUDA cores are relatively simple. They can perform basic arithmetic operations like addition, multiplication, and fused multiply-add, FME. But what makes them powerful is their sheer number and their ability to work in parallel. Alongside these cores, modern GPUs also include specialized units for specific tasks. Tensor cores accelerate AI and machine learning operations, while RT cores handle ray tracing calculations for realistic lighting. Surrounding the GPU chip on the graphics card are several other critical components. First, there's the memory system. Modern graphics cards use specialized high-bandwidth memory, often called DDR6 or DDR6X. Unlike the system RAM in your computer, GPU memory is designed specifically for the massive bandwidth requirements of graphics processing. A high-end graphics card might have 24 GB of memory with a bandwidth of over 1 TB per second. That's enough to transfer the entire contents of a Blu-ray disc in less than 50 seconds. This high-speed memory is crucial because graphics processing is extremely data-hungry. The GPU needs to constantly access texture data, vertex information, and other assets to render a scene. The memory chips communicate with the GPU through a wide memory bus, typically 256 to 384 bits wide in high-end cards. This allows the GPU to read and write large chunks of data simultaneously, further enhancing performance. Another critical component is the power delivery system. Modern GPUs are power-hungry beasts, with high-end cards drawing 300 watts or more under load. That's more than 3 times what a typical CPU consumes. To deliver this power reliably, graphics cards use sophisticated voltage regulation modules, VARMs, that convert the 12 V impulse to the lower voltages needed by the GPU and memory. All this power consumption generates a lot of heat, which is why graphics cards have elaborate cooling systems. Most cards use a combination of heatsinks, heat pipes, and fans to dissipate heat. The heatsink makes direct contact with the GPU chip through a layer of thermal paste, while heat pipes, copper tubes filled with a phase change liquid, efficiently transfer heat away from the chip to the fins of the heatsink. Fans then blow air across these fins to carry the heat away. Some high-end cards even use vapor chamber cooling, which is essentially a flat heat pipe that covers the entire GPU. And for extreme performance, there are liquid-cooled graphics cards that connect to a radiator and pump system. The final major component is the PCB, or printed circuit board, which ties everything together. This multi-layer board contains all the electrical traces that connect the GPU to the memory, power delivery system, and external interfaces like the PCI connector and display outputs. Now that we understand the physical components, let's explore how a GPU actually processes data. The key to GPU performance is parallelism, the ability to perform many calculations simultaneously. GPUs use an architecture called SIMD, single instruction, multiple data, or its more flexible variant SIMT, single instruction, multiple threads. In this model, the same instruction is executed across many different data points simultaneously. For example, when rendering a 3D scene, each pixel on your screen needs to be calculated independently. With a 4000 display, that's over 8 million pixels. Rather than processing them one at a time, a GPU can work on thousands of pixels simultaneously, dramatically speeding up the rendering process. This parallel processing is organized into a hierarchy. At the lowest level, individual threads execute on CUDA cores. These threads are grouped into warps of 32 threads that execute the same instruction in lockstep. Warps are further grouped into thread blocks, which are assigned to streaming multiprocessors. Finally, the entire workload, called a grid, is distributed across all available SMs on the GPU. This hierarchical approach allows for efficient scheduling and resource allocation. The GPU's scheduler can assign thread blocks to available SMs, ensuring that all parts of the chip are utilized effectively. Let's look at a concrete example of how this works in practice. When rendering a 3D scene, one of the first steps is transforming all the vertices from their local coordinate space to world space. This involves multiplying each vertex by a transformation matrix. In a typical scene with millions of vertices, this would be a massive computational task for a CPU. But for a GPU, it's perfect. The same matrix multiplication needs to be performed on each vertex independently. The GPU can assign thousands of threads to process different vertices simultaneously, completing the task in a fraction of the time it would take a CPU. This same principle applies to many other graphics operations, texture mapping, lighting calculations, pixel shading, and more. They all involve performing the same operation on many different data points, making them ideal for GPU acceleration. Beyond graphics, this parallel architecture makes GPUs excellent for other computationally intensive tasks. Cryptocurrency mining, for instance, involves performing the same hashing operation millions of times with different inputs, looking for a specific pattern in the output. This is perfectly suited to GPU computation. Similarly, machine learning and AI workloads often involve large matrix multiplications and other operations that can be parallelized. This is why GPUs have become essential tools for training neural networks and other AI models. Modern GPUs also include specialized hardware for these non-graphics tasks. NVIDIA's Tensor cores, for example, are designed specifically to accelerate the matrix operations common in deep learning. These cores can perform mixed precision matrix multiply accumulate operations much faster than traditional CUDA cores, dramatically speeding up AI training and inference. Ray tracing cores are another specialized unit found in modern GPUs. Ray tracing is a rendering technique that simulates the physical behavior of light to create highly realistic images. It's computationally intensive, requiring the GPU to trace the path of millions of light rays as they bounce around a scene. Dedicated ray tracing hardware accelerates this process, making real-time ray tracing possible in games and other applications. The software side of GPU operation is equally complex. GPUs are programmed using specialized APIs like DirectX, Vulkan, or CUDA. These APIs allow developers to write code that runs directly on the GPU, taking advantage of its parallel architecture. Shader programs written in languages like Haskell or Gliels define how the GPU processes vertices, pixels, and other elements of a 3D scene. These programs are compiled into machine code that runs on the GPU's cores. For non-graphics applications, frameworks like CUDA, OpenCL, or Direct Compute allow developers to use the GPU for general-purpose computing tasks. This is often called GPU, general-purpose computing on graphics processing units. The future of GPU technology looks incredibly promising. Each new generation brings significant improvements in performance, efficiency, and features. We're seeing GPUs with more cores, higher clock speeds, and more specialized hardware for tasks like AI and ray tracing. Memory technology is also advancing rapidly. New standards like DDR6X and AP3 offer even higher bandwidth, allowing GPUs to process more data more quickly. And architectural innovations continue to improve efficiency and flexibility. AMD's APUs and Intel's integrated graphics are bringing GPU-like parallelism to traditional CPUs, while NVIDIA's acquisition ARM suggests a future where CPU and GPU architectures are more tightly integrated. As AI and machine learning become more prevalent, the line between graphics processing and general computation continues to blur. Future GPUs will likely be even more versatile, capable of handling an even wider range of computational tasks. In conclusion, the modern GPU is a marvel of engineering, a massively parallel processor capable of performing trillions of calculations per second. Its unique architecture makes it ideal for graphics rendering, AI, scientific computing, and many other applications that benefit from parallel processing. From the thousands of cores working in concert to the specialized hardware for ray tracing and AI, every aspect of a GPU is designed for maximum performance in parallel workloads. And as technology continues to advance, we can expect GPUs to become even more powerful and versatile in the future. Whether you're a gamer enjoying the latest titles, a content creator rendering complex 3D scenes, or a researcher training AI models, the GPU is an essential tool that makes modern computing possible. Understanding how these incredible devices work gives us a deeper appreciation for the technology that powers our digital world. So next time you're marveling at the realistic graphics in a game, or the speed of an AI application, remember the incredible parallel processor working behind the scenes, performing trillions of calculations every second to make it all possible.